This is the second of two videos helping with homework problems where you have to do an integration to find something about an electric field. In both cases, the previous one was homework problem number 27. That was easier. You should look at that one first if you don't get this video immediately. This is problem 33. It's more complicated because two dimensions are involved. So the setup is interesting. A semi-infinite non-conducting rod with uniform linear charge density. The first year I taught this course, one of the students in the class said that was going to be her criterion for whether or not she accepted admission to a university. She was going to ask their physics department, do you have a semi-infinite non-conducting rod with uniform charge density? Because if you don't, then I'm not going here. So of course, not possible, but it's a mathematical construction and we can do the integral. So you have this semi-infinite. Semi-infinite means it terminates on the left, but it goes on forever on the right. The charge density is known. Q and L cannot be given because they would both be infinite, but the ratio of Q to L can be given as lambda, the linear charge density, which means that's how much charge would be in a meter. If you took 1 meter of this, if say this is 4, that means in 1 meter of this you'd have 4 coulombs of charge. There's a point P at the end, the left end of the rod, and directly below it a distance R. I don't think there are any numbers given in this, so the whole thing will be done in letters. Clearly a positive charge here, even if it is semi-infinite, will create an electric field here that points down and left. What they want you to prove is that this angle of this electric field is always 45 degrees away from the horizontal and of course up from the vertical. For any R, it doesn't matter how far away you are, this angle should always be 45 degrees. And it makes sense that it doesn't matter how far away you are because this is semi-infinite. So all distances would be the same proportion to something that's semi-infinite. It's not immediately clear why it should be 45 degrees. So in order to prove that, you have to find each component separately, the horizontal leftward pointing component and the downward vertical component, and prove that they have equal magnitude. Once you've done that, if you show that this EX and this EY have the same magnitude, the same exact formula in terms of the givens, then you've shown that this angle is always 45 degrees. So the method is the same as in the previous one. When there's no Gaussian symmetry, you have to pick a representative little bit of charge. That's all of this is considered very infinitely thin, so it's the same distance from here. So you pick up a little block of charge that's all the same distance from point P. Then you look at the little electric field that it creates. And not only that, we have to look at the components of this. This points down and left, so it will create a part that points down and a part that points left. And we want to find those separately. Okay, so let's start setting this up. Let's forget this for a while and look only at constructing an expression for this dE, for this little bit of electric field created by the little bit of electric charge. So dE, by Coulomb's law, the formula for a point charge, we can use the Coulomb's law constant K times the charge, which will be dQ, right? dQ stands for a little bit of charge, divided by the distance squared. We'll use letter little r for distance. And notice that's not a letter that's given, which means it cannot be in our final answer. And that distance would be, and what I draw in black will be the things that we draw, that we add. Red is the charge in the field, brown here for the r is the distance given as capital R, and in black we'll draw what we add. So we'll draw a straight line for this distance from there to there, and we'll call that lowercase r. Okay, in that case the little electric field dE would be k dq over r squared. Well, there are some problems here. We have two variables that will change, and what we'll do is come up with an expression for this and look at how it changes as we look at all the dq's starting here and going to the right. Okay? So as we do that, think about what will change. Well, clearly r will get bigger. Okay? So this will change. But then I'm winding up with two variables. The variable of integration looks like it's going to be q, but then I have r changing as I look at all the different dq's. So that's unacceptable. We can't do an integral like that. So we have to construct something that involves only one letter of integration, only one variable, and we'll attack the r first. We're going to start with a dq here, and we're going to look at one here, 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 and figure out what dE they create from here all the way as I add them all up, starting here and going on forever. So as I've said a couple of times, your variable of integration in this chapter is always going to be a spatial one, like x or r or theta. In this case, since the thing that we're looking at, the little piece, moves in this linear fashion along this axis, its position is going to be our variable of integration. So we immediately draw an x-axis going like that. That's the plus x direction. And of course, right here, the easiest thing to do is define that as x equals 0. So I'm going to set up an integral where x starts at 0, and that's going to be the bottom number on my limit of integration, and the upper limit is going to be the infinity symbol, because this goes on forever. So once you've done that, this thing has a position, x. And since this is x equals 0, that means this distance here, from here to here, is x. So now x is not only a position, it's a distance, since that is x equals 0. So look what I've created. I've created a right triangle with r, little r, as the hypotenuse. So note, r equals the square root of x squared plus capital R squared. The hypotenuse equals the square root of this side squared plus that side squared. Pythagorean theorem. So dE would be k dq, and instead of r squared, we're going to take this and square it, and conveniently that winds up being the x squared plus capital R squared. Okay, so there's an expression with for dE, for this little electric field, in terms of a very convenient variable of integration, which starts at 0 here and is along the line of all the little dq's we're going to add up. But it's not going to be very good for an integral, because I've got that typical problem that arises of more than one variable. I've got two variables. So I need to do what I did in the previous video with the simpler problem and find out some way to get dq replaced with a dx. And the way we do that is we use the width of this. And if this is the x direction, then a little width would be represented by what symbol? What symbol would be represented by dx? And we've given to us a lambda. That's considered given, that it has a uniform linear charge density. And what that means is that's Q over L for any length you take. It's the charge you get divided by the length. That's what that means. So we can do that with what we call infinitesimals here, these very little bits. dq over dx. That is lambda. So dq over dx can be replaced with lambda. So dq, solve this for dq, can be replaced with lambda dx. If you work in a mathematical science, you want to get very used to the idea of an amount being a density times some kind of spatial quantity. It could be a linear density times a linear distance. It could be an area or surface density times an area. It could be a volume density times a volume. So it could be linear density times a length. That's what I should say. Okay, so you want to get used to those three-dimensional things, length, area, and volume, using the densities this way. Here we're using really, really small ones, so we have the d's. Okay, so we now have an expression for that little bit of electric field that is usable. K, and then in place of the dq, we now have lambda dx, right? A little amount of charge is linear density times a little length, divided by the distance squared, but we use the Pythagorean theorem to write the distance squared not in terms of this new variable r, but in terms of the given capital R and the variable of integration x. So now look what I have here. I have something that could be used in an integral because the only variable in it is x. K, lambda, and capital R are constants. All right? So you might think, well, we could just sum this all up, put an integral sign in front of it, and we'd be done. Unfortunately, no, because this is in the x direction, but it creates an electric field that points down and left, which means that as this little dq moves out farther and farther away, like if you start with the very first dq here, it creates an electric field pointing straight down. And as you keep picking dq's farther and farther away from that, bigger and bigger x values, the little pieces they contribute are going to go like this. And then the farthest one away, very, very far away, will get very, very close to creating one that is horizontal. And you might already guess then, well, probably the average is right in between, and that turns out to be right, but we haven't proven it. The very first dq creates a component, a little dE that points straight down. As you go farther and farther, the little electric fields go more and more like this until you approach horizontal, but you never quite get there. All right. In other words, you cannot just integrate this and get an answer because that dE is pointing in different directions. Okay, you can't sum up things that point in different directions. All right, so what do? Well, we never really wanted that dE by itself as a thing in the first place. That's not what the problem's asking us to find, although we could eventually get it. But whether we need to find the total electric field or just each component separately, we're still going to have to find the components. Even if we wanted the total electric field, we still have to find each component separately. That's the way we have to handle vectors. So let's look first at the x component. The part of this dE, this points left and down, so the part that points left. So we're going to look at this part and call that, of course, dEx, the part that points left. And there's a second part. Oh, I color-coded that differently. I wanted horizontal to be blue and vertical to be orange, so we'll write over that. Okay, there we go. There's the horizontal part, and this little electric field also has a vertical part. Don't let the little d's confuse you. You don't really look at them, you look at the second part. This is saying an electric field pointing down and left is made up of two parts, a part pointing left and a part pointing down. The strength of the part pointing left is E sub x, and the strength of the part pointing down is E sub y. The little d's just mean that these are small. These are very small amounts because we start with a very small amount of charge. Okay, so I've written down what we brought from the previous work. This distance here is important in our formula for the dE, and it's written, it can be used, you can use the Pythagorean theorem to write it this way. Okay? The dE, we wound up writing it like that. K times the little amount of charge, lambda dx, divided by this distance squared. Okay, so that's what we've seen before. But we want to add up all of this. We want to do this. The actual Ex equals the integral of summing up all the little Ex's. All the little Ex's. That's what this means, little bits of Ex. So that's the integral we want to do. We only want to look at this part here, the horizontal part. So we need an expression for that. We only have an expression right now for the hypotenuse, not for this. Fortunately, we can use, I don't know, I guess this is a transversal thing, something from geometry, and the definition of trig functions to get just this part in terms of the rest of the problem. So let's go through the steps here. Let's call this angle theta. And of course, this makes a right triangle. So look what we've got here. We've got a right triangle, and this is the hypotenuse. The big dE is the hypotenuse, and we want which side? The opposite or adjacent side, if we're doing the blue. We want the adjacent side. Okay? So we could use dEx equals dE cosine theta. We can replace this, take this here and put it in for that there. We can put this in for dE, and it's looking better and better. We're going to have an integral. In fact, let's do that. So dEx equals the dE, okay, k lambda dx over x squared plus capital R squared, and then cosine theta. Okay, this should, I hope, make sense, especially if you review the video. This here is the hypotenuse, dE. We arrived at that before, but we only want this side of it, the adjacent side, so we multiply it by cosine theta. We have the same problem we had before, though. We run into this problem. We have two variables now. We have theta and x, because clearly as x gets bigger and we go this way, and look at the dq's going this way, this theta will get smaller. So this is the two variable problem again. So what are we going to do about that? Well, we're going to use something from geometry. This line up here is parallel to this line down here, and this is a transversal, so you can put an angle there, and you can see that's going to be the same angle theta. If you really need to prove it, you could draw it out and show that that's a transversal, and you have whatever those are called. Okay, so that's theta there. So we're going to use what cosine theta is from the top here. Cosine theta equals, let's see, which one is cosine? Here's the right angle, here's the hypotenuse. Cosine is what? Adjacent over hypotenuse. So use cosine theta equals adjacent side, or x, over the hypotenuse side, or square root of x squared plus capital R squared. All right, and so you're going to replace this cosine theta with this. And look what happens. All the bad variables are going away. Q is gone. We're getting rid of theta this way, and we get, so dEx equals k lambda dx over x squared plus r squared, capital R squared, times x over square root of x squared plus capital R squared. This looks like a big mess, but you can actually identify the different parts of it. That's the Coulomb's law constant. This is dq, the little amount of charge, and this is the distance squared. So this is the small electric field that's created. K times charge over distance squared, little r squared. Okay? But we don't want that whole thing. We only want the horizontal part, the adjacent part, the cosine part. So we multiply by cosine of theta. And you have to go back to the diagram. We can't use this theta here, but it's the same theta as it is up here, and cosine theta here can be written in terms of sides. Cosine is the adjacent side, here the adjacent side, over the hypotenuse. All right, now to actually do an integral, you'd want to kind of combine things and simplify them, put the dx at the end. So you'd write this as k lambda, okay, and then x on top, over, and then combine those and get x squared plus capital R squared to the 1 to the 1/2, so this becomes to the 3/2, and then dx at the end, and you would integrate this thing. And you could put the k lambda out front because it's a constant, and you start at x equals what? Well, we start at x equals 0, and we stop when? We could go from x equals 0 to when? Do we go to L? Does this thing have a finite length? And the answer is no. We go forever, so we have to put an infinity symbol up here, which means you're in BC calculus. It's not something that's done in AB. You're in BC, you're doing what's called an indefinite integral that has infinity at one end. And the way you do that, it's not complicated, at least I don't think so after teaching it for 15 years. It's not complicated. You find the antiderivative of this. You plug in 0, but you also, for this one, you don't plug in infinity. That's not a thing. But you look what happens as x gets bigger and bigger and bigger. In other words, you take the limit as x gets bigger and bigger and bigger, and that integral is solved in the solutions handout. So this, I won't do the integral. It's a straightforward integral with a u substitution because you have x squared here and you have its derivative up top, give or take a constant. So this can be done with a straightforward u substitution of u equals x squared plus capital R squared, and I won't go through and do the integral. What you get is that horizontal component equals k lambda over capital R. Okay, but we had to prove that this angle was, that the angle, let me get the original. We had to prove that this angle was 45 degrees in all cases, no matter what capital R was. So to do that, we have to show that EY equals the same thing. Okay, so C, for component EY, we do the same thing. Use the same thing for DE, which would be k lambda dx over x squared plus capital R squared. That's Coulomb's law. K times the little charge divided by the distance squared. Okay, times, but in this case, I don't think I have to redraw the diagram or show you all the steps. I think it's straightforward enough. You can use the sine component. So you have to go back to this diagram and see what's the sine component. Let's see. There's this diagram. Okay, there's our theta, and the sine component would be opposite over hypotenuse. So the sine part would be opposite side, which is capital R, over the hypotenuse, which is square root of x squared plus capital R squared. You can see this looks extremely similar. Everything is the same as the previous. This is DEY. Everything is the same as the one for DEX, with one change. Instead of an x here for the adjacent side over the hypotenuse, it's capital R for the opposite side over the hypotenuse. But that changes this integral into an integral that winds up being of this form. This is not the actual integral, this is the form. 1 over x squared plus capital R squared dx, which is of the form du over, or I'm sorry, to the 3/2. There we go. 1 over x squared plus capital R squared quantity to the 3/2. And this is of the general form u squared plus 1 to the 3/2. It can be converted to that form, and if you want to solve the integral, you have to use trig substitution, which I explained in class, and if you want me to do a lesson on that as a video, then I can. So that's how to do the problem. There's one last a wrinkle to it though. If you're happy with that, you can stop the video now. But there's another way to do it so that you don't actually ever have to write any trig functions. It's absolutely mathematically equivalent, but you can skip writing the trig functions, and that's to use similar triangles. This triangle up here is similar to this triangle down here. So instead of going through all the rigmarole of writing cosine theta, you can just use the ratio of sides, that dEx over dE is the same ratio as x over r. You can use that and arrive at the same thing. So you can use the ratio of similar triangles. If you like that, it would be a little bit faster, and you would skip having to write sine and cosine and then going up here and figure what they are. Different students prefer it different ways.